This is podcast 4.1. Podcast 4.1 is all about reaction types, electrolytes, and solutions kind of in general. So we're just going to, most of this is a review. We'll just whip right through it. Electrolytes, there are strong and weak ones. And basically, it's all a function of how many ions do they produce. Strong acids, things that are very, very soluble are going to be strong electrolytes. Things that don't produce many ions. Tap water stays water. Vinegar is a weak acid, so it does not produce very many ions. You guys need to remember your strong acids versus your weak acids. Okay? And your strong acids are pretty easy. Your strong acids are a function of knowing these three: Hickel, Hibber, and High. The friendly acids. Hickel, Hibber, High are all strong acids. Any of the other acids you would see that are binary would be, of course, weak. So hydrofluoric is not one of these three, therefore it would be weak. The other rule you need to know is if the oxygens outnumber the hydrogens, that means greater than. If the oxygens outnumber the hydrogens by 2 or more, then it is strong. So for example, H2SO4, sulfuric acid, the oxygens outnumber the hydrogens by 2 or more, so it is a strong acid. Weak acids are going to be all the other ones. Acetic acid, formic acid, phosphoric acid, H3PO4 would not be strong simply because the oxygens don't outnumber the hydrogens by 2 or more. Bases, you remember that bases are pretty much metal hydroxides. Weak bases are things that don't dissolve very well, or are things like ammonia. If you'll just remember that ammonia is NH3 and that it's a weak base, that will carry you through. All right, now, you have probably learned in the past there are 5 types of reactions. And I'm going to tell you that that was probably true back when you took Chemistry 1. But I'm going to tell you that for the most part, there are really only 3 reaction types. There are precipitation reactions where you make a precipitate. There's an acid and a base where you always make a salt and water. It's called a neutralization reaction. And then you have this very broad range of reactions that are called redox reactions. So this one is a precipitate reaction because it makes silver chloride. This one is an acid base because it makes a salt and water. Both of these, before, you probably would have learned, are double replacement reactions. Then you had 4 other types of reactions: synthesis, decomposition, single replacement, combustion, and all of those reactions are actually this kind down here: oxidation reduction reactions, or what we will come to know and love as redox. So why didn't we tell you this before? Why did we lie to you in Chem 1? Well, imagine teaching you that there are only 3 kinds of reactions and trying to use all those rules. It's much simpler to kind of break up the redox reactions into synthesis and decomposition, single replacement, and combustion, when actually they're all pretty much the same thing. All right? Now, you guys need to memorize some solubility rules. These solubility rules are from your book, and these are solubility rules that you can memorize, but they're not the friendliest in the world. Okay? So look them over, and then I've actually got one more set of solubility rules that's actually in your lab manual there towards the back that are even simpler, and this is those. The most important rule is know your always. Okay? Your always. Your always are ammonium, nitrates, acetates, and chlorates. And anything in group 1. So sodium, potassium, lithium, rubidium, any of those things are going to be soluble. If you know those, if you know your always, then that's going to cover 90% of stuff. All right? The second thing is there are certain things that always come up as being insoluble. For example, silvers, mercuries, leads, carbonates, phosphates, and fluorides, they will 9 times out of 10 be insoluble unless, and it happens to be rule number 1. So if it's ammonium carbonate, it's okay. Ammonium phosphate, it's okay. If it's lead acetate, that's okay. So if you let rule number 1 rule your life, then you'll remember your solubilities. All right? So then you can look at rule number 3 and rule number 4. You guys really just need to memorize these so that you can use these. All right? When we write equations, and some of y'all may have done this in Chem 1 and some of you may not, you can either write out an equation like you're used to, or you can split everything that's aqueous into ions. So in the equation above, you've got silver nitrate that's aqueous. Well, silver nitrate doesn't look like that in solution. Silver nitrate actually splits apart. So would the sodium chloride. It would split apart into the ions. They would be floating around the water. They don't hang out together. They actually stay separate. So it would be better to show it thusly, where you have all the things that are aqueous split up into their component ions. Notice the only thing that stays together is the silver chloride. And why is that? Well, because it's not aqueous. It's actually a solid. So this is called a complete ionic equation. And all you have to do to make a complete ionic equation is take anything that's aqueous and split it up. You can then come up with a net ionic equation. In other words, what is left over in the equation. So let's go back real quick. All right, so this is your job. I want you to identify the things that are exactly the same on the left and the right. What are the things that don't change? This guy right here, cross him out. Nitrate, good. Do you see anything else that doesn't change? Sodium on the left and sodium on the right. Good call. And what you're left with is what really happened in the reaction. Silver ions combined with chloride ions and made silver chloride solid. That is the truth. That is the true meaning of what happened in that equation. So we can write what's called a net ionic equation by canceling out the spectator ions, the things that are doing nothing. All right, now, the solubility rules will help you in the precipitation reactions, the acid-base reactions, the neutralization reactions. Those are simple. The hardest ones are, in all honesty, the redox reactions or the oxidation-reduction reactions. So one thing you have to do to get ready for that is you have to be able to assign oxidation states. Okay? So you guys need to get these rules down in your notes. If you guys can get these rules down in your notes, then we will actually practice assigning oxidation states in class. Now, the important thing here is, what if you stick two things together? So, in other words, what if you stick SO2 together? Then how do you decide what the oxidation state is? Well, and why would it have an oxidation state? Because it's covalent. Well, you have to remember that one thing is always more electronegative than the other. One thing is more lustful for the electrons than the other. So the other one's going to take on a negative oxidation state, meaning it's stealing the electrons. The other thing takes on a positive oxidation state, meaning it loses electrons. So fluorine, the reason why fluorine is always a -1 right there is because fluorine is the most electronegative. So whoever you put fluorine up against, fluorine will always take the electrons. So in the case of sulfur dioxide, you would look at the periodic table and the periodic trends, and oxygen is going to be a more electronegative than sulfur is. So out of these two, sulfur and oxygen will get the negative oxidation state, and sulfur will get the positive. All right, a couple things to remember that you want to go ahead and get in your notes. Leo says Gur. Leo says Gur means losing electrons. Losing electrons is oxidation. Dun, 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 dun. And gaining electrons is reduction. Right? The oxidizing agent, and this is something we'll practice in class. The oxidizing agent is What was reduced? Meaning, the oxidizing agent is the thing that stole the electrons, the thing that took the electrons in the first place. The reducing agent is the thing that was oxidized, or the thing that lost the electrons. So the oxidizing agent, what does it mean to oxidize? Oxidize means to lose electrons. So the thing that does the oxidizing is the thing that steals electrons away from someone else. Okay? So when we look at something, we want to say, well, who was the oxidizing agent? It was the thing that was reduced. It's always on the left-hand side of the arrow. The reducing agent is the exact opposite. The reducing agent is the thing that received the reducing agent is the thing that gave the electrons away in the first place. So it was the thing that was oxidized. All right? I know it's kind of confusing, but you will get used to it. The thing that was reduced is the oxidizing agent. The thing that was oxidized is the reducing agent. And that'll do it for podcast 4.1. See ya.